Welcome back to MLT 130. This is the lecture on body water and fluid balance. For the introduction, we need to know that electrolytes are charged particles called ions. Anions are negatively charged or migrate towards an anode, and cations are positively charged and move towards a cathode. So this is our little diagram here to help us remember. Cats are good, so positive, cations. Onions are bad, so negative, anions. Electrolytes are essential components for numerous processes throughout the body. And I'll just read through a few of these, but you can read through all of them on your own. So things like sodium, potassium, chloride help with volume and osmotic regulation. Potassium, magnesium, and calcium help with myocardial rhythm and contractibility of our muscles. Um, Bicarbonate, potassium, and chloride helps with acid-base balance of the body. Things like calcium, magnesium, and potassium also help with coagulation. So the body has systems to monitor electrolyte concentrations in order to keep them in a very narrow range. And some of the ways that the body does this is through blood pressure, the amount of water in the body, and osmolality. Our major electrolytes that we routinely measure in the lab include sodium, potassium, chloride, and bicarbonate. Some information we need to know about the water in the body is that in the adult body, about 60% of the mass of the body is water. Water is the solvent for all body processes. And remember, solvent is the liquid part that the solute is dissolved in. If you think back about the difference between a solute and a solvent when we were in lab math. The TBW, or the total body water, is equal to the intracellular fluid, or the ICF, plus the extracellular fluid, or the ECF. The intracellular fluid is about 2/3 of the total body water, and the extracellular fluid accounts for about 1/3 of the body's total water. So then the extracellular fluid is divided between intravascular intracellular fluid, or plasma, and the interstitial cell fluid. A big portion of plasma is water. Plasma is about 90% water. So something we need to know and understand when we're talking about water and fluid balance is osmolality. Osmolality is the concentration of solutes per kilogram of solvent, and this is dependent on the number of particles in a solution, not the kind of particles or the size of the particle. Okay, so we're worried about the number of particles. Virtually all ions and neutral substances contribute to plasma osmolality. So we have a challenge here. We need to think of the difference between specific gravity, like we talked about in urines, and osmolality test on urine specimens. So what would be the difference? Think about it real quick before we go on and get the answer on the next slide. The answer is that the specific gravity is affected by both the number and the size of the particles that contribute to the concentration, whereas the osmolality is dependent on only the number of the particles, independent of the size or the kind. But both tests are measurements of concentration. So what are some of the samples that we can use to determine osmolality? We can use serum samples, or we could use urine samples. And there's a couple different methodologies that we can use for measurement. We can use freezing point, or we can use vapor pressure using an instrument called an osmometer. The normal range for serum is between 275 to 300 milliosmoles per kilogram, but urine, the ranges are a little harder to establish and can range from 50 to 1400 milliosmoles per kilogram. So here's a quick question to review what we've just learned. Osmolality can be defined as a measure of the concentration of a solution based on the And pause the video at this time. Try to answer it on your own before you continue on and get the correct answer. Is it A, B, C, or D? The correct answer is A, number of dissolved particles independent of size. So let's talk about regulation of osmolality. Regulation of osmolality indirectly affects sodium and associated ion chloride, which accounts for about 90% of osmotic activity. The hypothalamus responds to osmolality. So this is a gland in your brain, the hypothalamus. The sodium balance regulates blood volume. Osmolality is regulated by changes in water balance, and blood volume is regulated by changes in sodium balance. The kidney also contributes to water balance. Osmolality is also maintained by thirst and ADH, or antidiuretic hormone, which is also known as vasopressin. It's both stimulated by the hypothalamus in response to an increased osmolality. ADH acts to increase water absorption in collecting tubules of the kidney. When there's an excess of water, osmolality decreases, suppressing both thirst and the hormone ADH. Drinking excess water causes hypoosmolality and hyponatremia in patients with impaired renal excretion. Hyponatremia is referring to decreased sodium. If water intake is inadequate, osmolality increases, or it's known as hyperosmolality, activating both ADH secretion and thirst. So let's sum it up all together with ADH and urine output. A dehydrated patient is going to equal thirst, which is going to increase the hormone ADH, which is going to decrease urine output. Your thirst is triggered by your hypothalamus. What is happening to make you not pee as much? An increase in ADH acts on the collecting duct. The membrane is more porous, thus you reabsorb more water back into the blood. A way you can think about it is you can think about babies that are dehydrated will have dry diapers. If a patient is well hydrated, they're not going to be thirsty, and they're going to have decreased ADH and an increased urine output. So think about it. You drink more, you pee more. The more decreased ADH causes your collecting membrane, duct membrane, to be less porous. Thus, the water is not reabsorbed back into the blood and it is peed out. In a patient with diabetes insipidus, they're known to have hyposecretion of ADH with the condition of diabetes insipidus. Symptoms include polydipsia, thirst, and polyuria. The glucose is normal, but there's a problem because of decreased ADH hormone. The decreased ADH hormone is typically from the destruction of the posterior gland or the hypothalamus. Just so we keep them separate, diabetes mellitus is increased glucose due to decreased insulin. Diabetes insipidus is decreased ADH. Both conditions have the three P's: polydipsia, thirst; polyphagia, increased appetite; and polyuria, increased urination. So here's just a review question on the information we've learned so far. All the following except will cause decreased urine osmolality. Is it diabetes insipidus, polydipsia, hypovolemia, or too little ADH? Pause the video, try to answer it on your own before you go on and get the correct answer. The correct answer is C, hypovolemia. That has nothing to do with decreased urine and osmolality. That's a condition where the liquid portion of the blood or plasma is too low. So we know osmolality is a measure of concentration. Thus, the more dilute the urine is, the less concentrated it is. Thus, the lower the osmolality. In a diabetes insipidus patient, the patients have decreased ADH. Thus, increased urine output means the urine is diluted and thus less concentrated. Thus, decreased urine osmolality. If a patient is always thirsty or has polydipsia, they drink a lot. They also have increased urine volume and will have a decreased osmolality. If a patient is hypovolemic, they have a low fluid volume in the blood plasma. Thus, they will have also a decreased urine volume. Thus, the urine will be more concentrated. The urine osmolality will be increased. Here is a really good visual for osmolality. This side is showing serum. This side is showing urine. So this is our sweet spot or our normal range. So this is about 270, 280 to 300, the normal range for serum. So here it lists some different factors that can affect osmolality. These are some reasons why serum osmolality could be decreased, and you see those fewer actual particles or parts in the serum. Here are some reasons that serum osmolality can be increased, and you can see it's much more concentrated. Same thing over here on the urine side. Here is our 50 to 1400 for our normal range. These are some factors that could cause urine osmolality to be decreased. Here's some factors. You can see this is more or increased. The reasons that they could be, or factors they could be, urine osmolality could be increased. Our blood volume regulation, the actual volume helps maintain blood pressure and ensures that there's blood perfusion to all tissues and organs. If we have a decreased blood volume, the RAS system is activated. You would have learned quite a bit about the RAS system in urinalysis. So does the RAS system help raise a person's blood pressure? Yes, that's the purpose, to increase blood volume, and thus it will also raise blood pressure. A decrease in blood volume or blood pressure causes the kidneys to secrete renin and also triggers the RAS system. Patients that have high blood pressure sometimes take blood pressure medicine called ACE inhibitors, which helps lower the patient's blood pressure. Here is just a diagram of the RAS system to help remind you. You can see on this blood pressure cuff, the patient's blood pressure is low. So as a result of that, the RAS system is going to be kicked off to try to raise that blood pressure. So through that process of the RAS system being kicked off, this patient's blood pressure is back in the green or within normal blood pressure ranges. The next thing we need to discuss is natriuretic peptides. These include ANP, our BNP, and our CNP, and all these are hormones, and they increase in response to increased volume expansion. They promote sodium excretion in the kidneys, thus help lower blood volume, thus functions as a diuretic. And of course, we measure BNP in the lab to help diagnose and monitor patients with CHF or congestive heart failure. Congestive heart failure patients will have an increased BNP level. Okay, we have one more review question. All the following are true of atrial natriuretic peptides except, is it A, B, C, or D? Take time to read all these options. Try to figure it out on your own before you go on and get the correct answer. Remember, this question was asking which are true except. So you're looking for the false statement. The false statement is it is decreased in patients with CHF or congestive heart failure. This concludes this lecture for MLT 130. If you have any questions or need any extra help, please don't hesitate to reach out.